Let's do the first problem in the calculator section. If t sub n is the nth degree Taylor expansion for 3e of x around x equals -2 and the error is less than 0.01 in the interval -2 to 0, minimize n. So the value we're trying to find is n, and the way we can do it is by using Lagrange formula. So let's write down the Lagrange formula. Is less than the absolute value of f to the power of n plus 1 of z times x minus a to the power of n plus 1 all over n plus 1 factorial. Now set that equal to less than 0.01. Now to find the error, you'll have to maximize these two terms on the numerator. So let's start off with the first one, f to the power of n plus 1 of z, and we have to plug in the values from the interval -2 to 0 in order to maximize it. So what is our f of 0 to x function? It is equal to 3e to the x. So let's differentiate that. If you differentiate that, it'll still be 3e to the power of x, and this will continue to infinity. So no matter what the f to the power of n plus 1 term is, you can safely assume that it will be 3e to the power of x. Now let's plug in a value from -2 to 0 that will maximize this. So that would be 0. So you can say the maximized value of the first term would be 3. Now let's do the second term. Absolute value of x minus a to the power of n plus 1. Since the Taylor series is based on -2, you can rewrite this as -2 minus a to the power of n plus 1. Now let's plug in a value from this interval -2 to 0 in order to maximize this. So if you plug in -2, that'll be 0. If you plug in 0, that'll be -2. So 0 will maximize this. So -2 minus 0, n plus 1. Because of the absolute value, it will turn to 2 to the power of n plus 1. Now let's bring this all together. 2n plus 1 over n plus 1 factorial is less than 0.01. Now if you plug into your calculator, you can get the minimum value of n, which should be 8. Now let's start the non-calculator section of this worksheet. So number 2. Given that f of x is equal to e to the power of 3x over x to the power of 5, express f prime of x as a Taylor series centered at 0. So there are multiple ways to solve this problem. So I've already written out path number 1, which is to find the derivative of f of x and then rewrite that as a power series. However, there is a more efficient way to solve this problem. So let's start out our path 2. So this path will find the power series of f of x first and then differentiate it. So f of x is equal to e to the power of 3x to x to the power of 5. To find the power series for this, you'll have to know how to rewrite e to the power of u as a power series. So let's leave the 1 over x to the power of 5 as is right now, and find the Maclaurin series for e to the power of 3x. So 3x to the power of n and factorial. And let's rewrite this so that it looks neater. 3n x. Now we can incorporate x to the power of 5 by subtracting from the exponent, and the denominator will stay the same. Now, you found a power series for f of x, however, the problem is asking you for f prime of x, so don't forget to differentiate. So how would you differentiate a power series? Well, it's actually pretty simple. So you rewrite the summation, and the only thing that'll be affected from the differentiation would be the x term. So what will happen to the x term is the exponent will be brought down, and your old exponent will be subtracted by 1, so you'll be left with n minus 6 all over n factorial. And that's your power series representation of f prime of x. However, it looks quite different from the solution we got from path 1. However, it still represents the same f prime of x. It's just written in a different form. Now let's move on to number 3. Find the interval of convergence for that. So you have multiple paths you can solve this with. So you can either go ratio, or you can solve it with root. And in this video, I will demonstrate it by using a root. But if you use a ratio, you'll still end up with the same answer, so it doesn't really matter. So let's set that up. As limit as n goes to infinity, nth root 7 to the power of n plus 1. Now we can just simplify this, get rid of the nth root. Now let's look at 5 to the power of 1 over n. If you plug in infinity, that'll just simply be 5 to the power of 1 over infinity and equal to 1. So you can just cross that off and not worry about it. And for x minus 2, since it's x and not an n, it won't affect the limit. So you can just bring that out with the absolute value sign. And what you have left is this. So you can't quite plug in infinity and find out what it's going to be equal to. So what you'll have to do is do L'Hopital's. Okay, let's do the top one first. For these kind of expressions, you'll have to use e to the power of ln. And remember that when ln is is to the power of something, you can just bring down the exponent. Now you can L'Hopital's it. So you differentiate the top and you differentiate the bottom. Now if you plug in infinity, that'll just be equal to 0, and your answer will be 1 for your numerator. Now let's look at your denominator. Let's look at the exponent only, since that has the nth term. Now let's do the L'Hopital's. Since if you plug in infinity for numerator and denominator, it will turn out to be infinity over infinity. So when you derive it, it'll be 1 over 1. So 1. But don't forget that this is the exponent of 7, so it'll actually be 7 to the power of 1. So you have 1, and you have 7 to the power of 1. Your limit will turn out to be 1 over 7 times absolute value of x minus 2, which is less than 1. Remember that when you're doing ratio or root test, if it's conversion, it is less than 1. So let's multiply 7 on both sides. Undo the absolute value. And then add 2 to the left and right. And you got your answer right there. You're done. That's what you think, but you gotta justify it. Justify it with numerical series tests. You're not done quite yet. So let's rewrite this. Let's plug in -5 first. X has -5. 5n. Plug in -5, that'll turn out to be -7n. And then 7n plus 1. Now you can break up the denominator because it's n plus 1. You can break that up into 7 to the power of n times 7. Now you can simplify it further. And at first glance, it looks like you can use AST. So let's do limit as n goes to infinity. Let's get rid of that -1 to the power of n. If you plug in infinity, that'll turn out to be infinity and not 0, so you can't use AST. But you could say this is divergent by divergence test. So if you use -5, that's divergent. So you wouldn't include it in your interval of convergence. Now let's do it as when x is equal to 9. Plug that in. 9 minus 2. And you can break up the denominator like you did before. This will cancel out. So you'll be left with this. And again, you can use the divergence test to prove that this won't be convergent. Because when you plug in an infinity, this will just turn into infinity. You wouldn't include x equals 9 in your interval of convergence either. So your interval of convergence would be -5 to 9, and then you're finally done. Number 5, express pi over 6 as a power series. So you should first know all 5 of your Maclaurin series. So I've listed them right here. So let's go through each one of them and see which one would work for this problem. E to the power of u, that wouldn't work. ln 1 plus u, that wouldn't work either. Let's look at cosine u and sine u. So for these, you'll have to plug in an angle to get a ratio. However, our answer needs to be an angle, so that wouldn't work either. And this is the only one we have left. And this is correct. That's because if you plug in a ratio, it will give us an angle in radians. So therefore, we'll use arctan. But what ratio should we plug in to get pi over 6? Let's draw out our unit circle. Pi over 6. Cosine and sine will be equal to √3/2, 1/2. And remember that tan is sine over cosine, so let's divide that, and you'll get √3/3. However, we'll just use this for the sake of simplicity. So plug that in. Write out your arctan Maclaurin series, which is this. Notice how the denominator it's not 2n plus 1 factorial. Don't get that mixed up because that is for sine u. So when you're writing either arctan or sine, be mindful of what you're writing on the denominator, since it can be either arctan or sine u. So it's arctan, you have to write 2n plus 1 on the bottom. That is a common misconception. Now we can plug in the x, which is, you could rewrite this as 3 to the power of -1/2. So move that on the bottom. The exponents multiplied by 2n plus 1. And you can simplify this further, and your answer would be this. And that's your power series representation of pi over 6, and you're done. Number 6, find the limit as x approaches 0. So there's a lot of types of problems like this, so you should know how to solve these. So what I did here is to convert ln x squared plus 1 into a power series, and then I wrote the terms out as n equals 0, 1, 2, 3, and so on. And then I found that x to the power of 2 and x to the power of 4 canceled out. So what you're left with is 1/3 x to the 6 minus 1/8 x to the power of 8, and then so on. And whatever term has x in it will turn to 0 because x approaches 0. However, the first term cancels out evenly. So you'll be left with 1/3 and 2, and all these stuff don't matter because it has an x in it. So as limit as x approaches 0, your answer will be 1/6. Right here I have listed 4 common misconceptions while solving power series problems. You can pause the video to have a better look at these misconceptions. Other than that, I hope the video helped you solve the problems in the worksheet, and hopefully you can solve the rest of the problems on the worksheet that was not solved in this video.